everybody, welcome back to my channel. So today we are going to talk about insertion sort. This is going to be the second video in the sorting playlist. Okay, if you have not checked out my earlier video about what is sorting and bubble sort, you should please check that out. Okay, so coming to insertion sort. Insertion sort is a sorting algorithm which is used to sort the data either in ascending order or in descending order, right? So what is something which is very unique about insertion sort? When it comes to applications in real life, insertion sorting is actually used. Insertion sorting is used whenever your size of the data is less. Meaning if you do not have very huge data and if you want to sort the data, then you can definitely use insertion sort. Or else if you have data which is partially sorted. Partially sorted means like you do not have suppose if you have say 10 numbers, all right, and let's say only 2 or 3 of those numbers are not in its correct position. Correct position means if you want that data to be sorted in ascending order and might be only 2 or 3 numbers out of those 10 numbers are not in its correct position as they should be if the data was completely sorted in ascending order. Such kind of data is called as partially sorted data, right? So if your data is partially sorted, or else if your data is not very large, if you have smaller data sets, in those cases, in practical scenarios, insertion sort is used. Okay, because the way the algorithm works, it is beneficial to use insertion sorting. Alright, so what are some common applications? You use insertion sort in financial applications. It is used in database management systems. It is also used in your gaming industry and in embedded softwares. So all these places, wherever the data sets are small and you have to sort them, there is insertion sort being used. So let's start. There is one more important property when we talk about sorting algorithms, and that is what is called as stability of sorting algorithms, right? We just discussed that insertion sort is very, has a practical applications when two scenarios. One is if your data is small size, that you have smaller size of data, or else if your data is already partially sorted, then your insertion sort is what is used in industry. Another important thing why insertion sort is practically and widely used in industry is because insertion sort is a stable sorting algorithm. Okay, so let's understand what does stability mean in a sorting algorithm and how it is really useful in real life scenarios, right? So stability in a sorting algorithm is defined as that if you say a sorting algorithm is stable, it actually preserves the relative ordering of the elements, relative order of the elements. All right. So what are we saying? That basically your stability in a sorting algorithm is defined as that it maintains the relative order of the elements. What does it really mean? Let's take an example. Suppose you have a bunch of names. In this, as you can see, I have 4 names here, right? One is John Smith, and this is the order in which I have it. I have John Smith, followed by Suzanne Lee, David Smith, and I have Emily Lee. So basically, this is my first name, okay? And this followed by the last name, right? Now, I want to basically sort this list, okay? By the end, I want this list to be sorted by both first name and last name. Okay, so what you will do, you must have also seen a similar feature when you actually go to this shopping sites, right? Amazon or Flipkart or Myntra. You have a lot of filters there, right? First you would say that you want to apply the filter based on price. Then might be you want to apply the filter based on might be the size of the product, right? So you can have this filters, right? So very similar thing in there also you're basically using a sorting algorithm which we had spoken in the first video of sorting playlist, correct? So here also I have a scenario where I have a bunch of names and I want to basically sort them in ascending order. First should be sorted based on both the first name and the last name, correct? So what I'm going to do is I'm going to first sort this list, okay? First sort them by my by the first name of these names. We have 2 possibilities, first name and last name. I want to sort them using first name first. So if I do it using ascending order, let's say you apply any sorting algorithm, what you're going to get, you're going to end up getting first David, because alphabetically D comes first, right? David followed by Emily, then you have John, and then you have Suzanne. right? That's how we are, right? So D, then you have E, J and S, right? No issues here. Now, I am going to again sort this list which I have obtained. I am going to sort it by the last name of the names, okay? Again, I am going to sort it using ascending order. So let's sort our, the names, right? Whatever we got here, what was it? We first sorted the names by first name, right? In ascending order. So we got David, Emily, John and Suzanne. Now let's sort these names again. Whatever sorted we have got here, let's sort it now by the last name, again using what? Ascending order, correct? So if it's ascending order, and you're going to use what? The last names, right? So the last names here, you have only two unique names are there. One is Smith and the other one is Lee, right? Alphabetically, actually L will come first before Smith. That means these names, Emily Lee and Suzanne Lee, will come first and then followed by David and John, correct? Now tell me, between Emily and Suzanne also, right? Because at the end, you are going to sort these names both by first name and last name, correct? So, and you want them to be sorted in what? Ascending order. So, ideally, what will be your expectation? Your expectation is that first Emily should come, because between Emily and Suzanne, E is the one which comes first alphabetically, correct? So, Emily Lee should come first, followed by Suzanne Lee. Agreed? After that, David Smith should come and then followed by John Smith, because between David and John, David is the one which comes first and then followed by John, right? To ensure this, suppose if I use a stable sorting algorithm, okay? Stable sorting algorithm is going to ensure the relative ordering of the input. Meaning what? See, between this, because you're going to sort it based on the last name in ascending order. First, it's going to say there will be these two Lees are going to come first, right? Now the question is, between Emily and Suzanne, which one should appear first in my output when you sort? Because you're using a stable sorting algorithm and there is a tie, right? Because you're sorting right now based on the last name. Now when there is a tie, because you're using a stable sorting algorithm, that algorithm is going to maintain the relative order. Relative order means this is your input, right, for sorting in based on the last name. In this, which has come first? Emily has come first, followed by Suzanne. So what I'm going to get first is Emily Lee is going to appear first in the output, followed by Suzanne Lee, right? Then next is you have Smith. Again, you have two entries for Smith. In the input, David has appeared first and then followed by John. So first David Smith is going to appear, then followed by John. Now if you look at the final list, this list is sorted both by first name and also by last name, right? As you can see, we are trying to sort these names based on what? Ascending order. So as you can see, the last name Lee has come first, right? In that also the names have been sorted. How? The first names have been sorted in which order? They have been sorted in the ascending order. Smith, okay, first David has come, followed by John. This was possible because we use stable sorting algorithm, which ensured that if there is a tie like this, it's going to ensure that the relative order of the input has been maintained in the output. These are the stable sorting algorithms, right? Then if this is stable, what would be the output for non-stable algorithm? But when you say you're sorting a non-stable, you're using a non-stable sorting algorithm, there is no guarantee that the relative ordering which is present in the input has been maintained. Meaning, see, if I'm using a sorting algorithm where whether that algorithm is not a stable algorithm, okay? Meaning that algorithm does not give me a guarantee of stability. So what will be the possibility is that it is possible that, okay, I'm going to sort in ascending order based on the last name. Fine. So obviously you're going to get the first two entries which will have last name as Lee. But there can be a possibility that first I get Suzanne Lee followed by Emily Lee. Now what has happened is because I'm applied a non-stable sorting algorithm, the order which was preserved in my input, which was present in my input, where Emily came first and then Suzanne, that is not preserved in my output. This is a scenario which can happen if you're using a non-stable algorithm. If you do this, if you can see, if I get something like this, my entire purpose of sorting them initially on first name has been gone for a toss. It was a complete waste of time to sort the names first using first name. Why? Because I use a non-stable algorithm. Anyways, at the output, this is going to get messed up, right? Might be first Suzanne appears first and then followed by Emily. Then I would not get the list which is sorted by both first and last name, which was our expectation, right? Even if you go to this Myntra sites and all, you would basically want what? You basically apply more than one filter, right? You sort it based on the price, you sort it might be based on the popularity, you also sort it based on the size of the product, right? Price, the size of the product, and the popularity. You want all these, you want those data which is now displayed, you want them to be sorted on all these three features, correct? In that scenario also, what in the background which is being used is a stable sorting algorithm which is being used, right? Insertion sort is a stable sorting algorithm, meaning it gives you a guarantee that the relative order of the elements in the input has been preserved when it appears in the output as well. So this is another big reason why insertion sort is very important and has a lot of practical applications in the industry. Now let's start with the algorithm. Let's start with the intuition of the insertion sort algorithm, right? So insertion sorting is actually based on the concept that you're going to divide an array, okay? Whatever array of integers or array of data you have, you're going to divide that data into two parts. One part is your sorted part and the another part is your unsorted part. So right now I have an array, so I can say I have a sorted subarray, right? And I have an unsorted subarray. Right? Now, in the process, as your algorithm proceeds, what you're going to do is the algorithm says, take an element from the unsorted part and place it in its correct position in the sorted subarray. Keep on doing this until there are no elements left in the unsorted subarray. Meaning what? See, to begin with, I can say that the first element which is present in my list or the first element present in my array of numbers belongs to the sorted subarray. So I have right now a sorted subarray whose length is what? Just one element, right? Why? Because when you have one element, that one element is always sorted, right? Whether it's ascending or descending order, correct? And we can consider the remaining part belongs to the unsorted subarray. That means initially my sorted subarray starts from index number 0 and ends at index number 0. Unsorted subarray starts from index number 1 and ends at the last index, which is n minus 1 if n is the total number of elements present in my array, right? This is how you will begin or initialize your algorithm. Then as the algorithm progresses, you are going to pick up one element, that is the first element which belongs to the unsorted subarray. Right now here I have 11 and I'm going to place this element which belongs to the unsorted part into my sorted part. So what will I get? Let's do this here. I would get 11 followed by 12, right? Because I have placed 11 which belong to the unsorted subarray into its correct position in the sorted subarray, what is going to happen is my sorted subarray is now going to expand by one element. So my sorted subarray is going from index number 0 to index number 1. Because my sorted part has expanded, obviously my unsorted part is going to shrink by one element. So now my unsorted element or unsorted part of the array is going to begin from index number 2 and should go to index number n minus 1. That means the remaining part which I have 13, 5 and 6. 13, 5 and 6. This is going to be my unsorted part and this is my sorted part. Correct? Now, we have still not finished sorting the entire algorithm. Let's continue. So now I'm going to pick up the next element which is at the start of my unsorted subarray and which is nothing but 13. This 13 will now has to be put, I want to put this 13 in its correct position in the sorted part. So when I do so, I'm going to have 11, 12 and 13, correct? So this is my sorted part. The remaining unsorted part is 5 and 6. In the next step, I'm going to choose 5, which is from my unsorted part and put in its correct position in the sorted part of my array. So now my sorted part will look like 5, 11, 12, 13 and then I have 6, right? So this is my unsorted part and this is my sorted part, correct? Now there's only last one element left in my unsorted subarray, which is 6, which needs to be put in its correct position. So when I do so, I would get 5, 6, 11, 12 and 13. Now there are no more elements present in my unsorted part of the array and that is why I can stop here and the algorithm has finally finished sorting all the elements in the in an ascending order. I'm trying to sort in ascending order and I finally got it, right? So what is the essence of the algorithm? You divide at any given point in time, your algorithm is going to divide the array into two parts. One part is your sorted subarray and the another part is unsorted subarray. You pick an element which is at the start of an unsorted subarray and try to place in its correct position in the sorted subarray. As you do so, what you're going to happen is you're going to expand your sorted subarray, obviously by one element. The size would be expanded by one element, and your unsorted subarray is going to shrink by one element. Keep on doing so until there are no more elements present in your unsorted part and your array is completely sorted. This is the insertion sorting algorithm. Now let's try to write code and dry run a particular example. Let's try to dry run the algorithm. So I have an array here 12, 11, 13, 5, 6, which I want to sort in ascending order using insertion sort. Let's give a name to this array as A. All right. And as we saw in the intuition part, let's have this part as your unsorted part and this is your sorted part, correct? So now what I'm going to do is I'm just going to have some variables. So I variable is going to basically signify the starting point of your sorted subhalf, right? And your index number j is basically going to say that the last part of the last element which is present in your sorted part, right? Right now we have only one element in our sorted part, so starting and ending has been basically given by j, right? But this I is this part, right? So I'm going to have here, I'm going to have a variable here, which is an integer variable key, which is going to store the value of the element which I have chosen from my unsorted half and which I want to place in its correct position into my sorted half, correct? So now I can see here the element which I've been chosen is 11. So 11 is going to be been stored in a variable called key. I have to place this key in my sorted part, right? So obviously my j is going to be I minus 1. This is the ending of my sorted half, right? So with this, let's begin. So let me try to perform something here. Let me try to compare the value which is a of j. What I'm trying to do is I'm going to compare the values which are present in my sorted half, okay? A of j. If a of j is greater than key, what is key again? Key is basically the value which I have chosen from my unsorted half of the array and I want to place this value in its correct position in the sorted part of my array, right? So I'm saying if a of j, if 12 is greater than 11, okay? If 12 is greater than 11, what I want to do is I want to a of j plus 1 should have the value of a of j. What is a of j plus 1? A of j plus 1 is this index. I want to store here the value as 12, right? I know you will have doubts why this is. Just hold on, you'll understand. So I'm going to say a of j plus 1 equal to a of j, and after doing that I'm going to decrement the value of my j. Why? Because I've already compared this a of j with the key value and now I'm going to decrement it. Now here j is now pointing toward minus 1, correct? Because initially this index obviously is 0. So when you do 0 minus 1 is nothing but minus 1, which is not a valid index, right? So I can stop here. After doing this, after I finish stopping, what I need to do is I'll do one more step. After performing this, once this is done, I'm going to do one thing. I'm going to say a of j plus 1. I'm going to give it the value of key. I'm going to say a of j plus 1 equal to key. Right now, what is the value of j? J is pointing to minus 1. Minus 1 plus 1 gives you 0. So basically, a of 0 will now have the value which is key. What is the value stored in key? In key, we had stored the value of 11. So now this will have, what we have right now here we have the value 11. So that means my array looks like this. It was initially, I had, I think 12, what was it? 12, 11. Right, 12, 11, and we had 13, 5 and 6, right? 13, 5 and 6, correct? We said this was our sorted part, okay, and this was our unsorted part. Unsorted part is starting with index number I, and this is where your j index is. After we did that, what we happened is here is what my 11 is and here is my 12. So what did we do? By doing this, we were able to place this 11, which we just took it from the unsorted part. It is now placed in its correct position, correct? So now we can see your 11 is here, 12 is here. This is now your sorted part. correct? Your I was initially pointing where? I was initially pointing to this index. Let's write the indexes here. This is index number 0, index 1, 2, 3, and 4. Initially, I is standing from index number 1. Now, after this one thing, after we have put the element which is an index number 1 in its correct position in the sorted part, let's increment the value of I. So let's now I is going to stand here. So let me say I is standing here, right? If I is standing here, what will J be? J is going to be I minus 1. So what does this signify? This signifies that this is my unsorted part of the array, alright? And from index number 0 to index number j, this is my sorted part of the array, right? According to the algorithm, now I have to place 13, okay, which I have chosen into my sorted part. So again, as we did for the number 11, we are going to store the value key. We want to store this number key which we have chosen from this unsorted part into a variable called as key, right? We are again going to check a condition. We are going to check, is A of j greater than key? Let's talk about this for a moment. See, j is nothing but signifying the last element in the sorted part, meaning that because you are trying to sort in ascending order, it means that this is the smallest element and this is the largest element, right? Because this half has already been sorted. This part has already been sorted, right? Now, when you want to place this number 13 in its correct position in the sorted part, yeah, then right now this, if you see 11, 12 and 13 actually is in its correct position. That means we do not need to shift or move any of the elements, right? But in the earlier example, in the earlier part, when we had these numbers 12, 11 and 13, let me just erase this. So we had initially, we had here 12 and then it was 11, right? What we had done is, this is where your I was and this is where your j was, right? To move 11 into the sorted part, we had to first make space for 11, right? That means you already have a sequence from 0 to j which is sorted. There is one element after j which needs to go in this sorted part. So that resulting elements are now from 0 to j plus 1, right? That means this key needs to be placed in the correct position, right? If I have to place this key in the correct position, think about this. Suppose if you had a sorted numbers like this, 2, 4, let's say 10, and let's say you had 12, and the number you want to place is 5. This is the number, this is suppose your key, and you want to place this key in the sorted part, right? Tell me what all changes you will have to do. Forget insertion sort for a second. What you will have to do? Where should your 5 be? See, after you place 5 in the correct position, what will your numbers look like? 2 is here, 4 is here, 5, 10 and 12, right? That means 12 needs to move, shift basically, 10 needs to shift, and then because you will shift them, then you can make space for 5. Agreed? So this shifting needs to happen, right? 12 needs to go. Right now, this number 12, let's write indexes 0, 1, 2, 3 and 4, right? Right now, at index number 3, we have 12. In the output index number 3, what do we want? We want number 10. That means from 10, this 10 needs to go from index number 2 to index number 3, and number 12 should go from index number 3 to index number 4. So that now at index number 2, we can place this number 5 or the key, right? To make space, to do the shifting, we are doing that by basically comparing this, right? That means if A of j, like if you can see here, A of j is number 12. This is nothing but the largest element in your sorted part, correct? Is A of j greater than 13? Is it? No. If it is not greater than 13, tell me, will any of the numbers, like this is j, right? J minus 1 is this. Tell me any numbers which are appearing before 10, 12, will those be numbers be greater than 13? No, because this part is already sorted in ascending order. So if this condition is not satisfied, which is the case, do we need to do any shifting? No, because the number key or whatever number we have chosen is already in its correct position. All you need to now do is increment the value of I. So now I is starting at here, right? That means now your sorted part of the array is become 11, 12 and 13, and your unsorted part is 5 and 6. If you have not understood this, might be you can just want to rewind and just have a look. If not, we are again going to look for number 5, right? So here again what I'm going to do is key equal to 5. Can you see? I want to move this into my sorted half. What is the last or the largest element in my sorted half? It is given at the index number j. right? Now tell me, if I have to move this 13, now between 13 and 5, I simply do a check. Is A of j greater than the key element? Yes, 13 is greater than 5. So how we are doing the shifting is very smart shifting we are doing. We are saying that already the element which is present here is stored in a variable called key. So if my A of j is greater than key, what I'm going to do is A of j plus 1 is going to give the value of j, and I'm going to decrement j. So I'm going to just say 13 and I'm going to decrement j. By doing so, just see, you have not lost any values, because see, what have you overwritten? You have overwritten 5 with 13. But is the value 5 lost? No, because the value 5 is already stored in a variable key equal to 5. So it's okay if you overwrite it. That's what the beauty of this particular process is, right? And because you have compared 13 with 5, now what you should be comparing? 12. That means your index j should basically decrement, and that is why I have j minus minus. All right. Again, I'm going to check 12 with whom? I'm going to check 12 with the key value, which I have chosen from the unsorted part to insert into my into my sorted part, right? From my unsorted, I have chosen 5, which needs to go into my sorted part. Now this number 5. Is 12 greater than 5? Yes, it is. It is greater. That means now I have to shift 12 towards what? Towards my right hand side, so that I can make space for the number 5. So now I'm going to do what? A of j plus 1. What is j plus 1? This position. This position is going to get a value of 12. Tell me, did you actually, by overwriting 13 with 12, did you actually lose 13? No. 13, if you can see, has already been mentioned here. We had already overwritten 5 with 13. I hope you're getting it. And because now we have compared 12 and 5, now I need to what? Decrement the value of j, and I'm comparing with 11. Now again the same thing, right? Between 11 and 5, what is it? 11 is greater than 5. What I need to do is I need to swap this and give a value of 11, right? Because I've given a value, let me just erase this. Because I've given a value of 11, have I actually forgot, like missed out the value of 12? No, because this number 12 is already present here, so I have not lost any kind of data by overwriting, right? And you're going to do what? Decrement the value of j. Now after decrementing the value of j was pointing at index number 0. Your j is right now pointing at index number -1, which is not actually a valid index. That means you can stop this process once you have reached j equal to -1, right? Once you do that, now I have to somewhere insert the value of 5. Where will you insert? Tell me right now. This is what your array looks like. Okay, let me write it properly. This is 13, okay, 11, 12, right? And your j is pointing somewhere here. Where should 5 go? 5 should actually go here. How can I get this particular index? By doing a of j plus 1. If I do now here, a of j plus 1 should be given the value of key. That means j plus 1 is this location. I should erase 11 and should write what? Number 5. What has happened? I have sorted the numbers from 5, 11, 12 and 13, right? So I can write here basically that 5, where is it? So basically I'm going to write here 5, right? 11, and what is it? 12, right? And 13. And because your I was here, which is pointing at 13, now you're going to increment it and move to 6, because this is the remaining element in your unsorted part, and your sorted part is now 5, 11, 12 and 13, correct? Again, we're going to do the same steps. Your j is going to point here, which is basically the largest element in your sorted part. Can you now perform the same operation? Absolutely. Now what we are going to do is again going to do a check between 13 and 6. Obviously, let's first store the value of 6 in a variable called key, right? So because 13 is greater, I'm going to replace this with 13 and decrement the value of j. 12 and 6, what is it? 12 is greater, so I'm going to give 12 here and decrement the value of j. 11 and 6, again 11 is greater, so I'm going to give here 11 and decrement the value. Now tell me, between 5 and 6, is 5 greater? No, so I stop my process here. So let's see what values we have right now here. So right now, this is what your array looks like. Let me write it up properly, 11 and 12. So I'm going to say 11 and 12. Okay. You stopped your array here. Why? The process we stopped here because 5 is not greater than 6. So can we again use the same formula which we used above? A of j plus 1 should get the value of key. What is j plus 1? This position. This position should get the value of key. Do we now have the entire array which is sorted? Yes, because we have completely exhausted all the elements which belong to the unsorted part. Your I was actually standing here. If you do I plus plus, this is going to point to index number n, and we don't have an index n, right? So now your sorted array looks like 5, 6, 11, 12 and 13. So the entire essence was divide the array into two parts and do the process of shifting. You're supposed to do the process of shifting, which is where I have depicted here, because you want to make space for this number. So how will you decide how to shift? You can simply do this. The trick is whatever element you have chosen to put into your sorted part, just store it in a variable, right? And they are free to simply override the values. Right? So if you see again this code, I'll be linking in my GitHub link, so you don't have to worry about it. Right? So in this insertion sort, again, I've written a function, right? So the first for loop is going to go from I equal to 1, I less than n, I plus plus. Now why I equal to 1? I think you know the answer. If you know, just comment down below. So what is I equal to 1? I equal to 1 because I am starting from my unsorted part of the array, right? So we initially said that the first element of my array, which is stored at index number 0, is going to be the sorted part, right? Initially, your sorted part of the array is index number 0 and ends also at index number 0. Unsorted part starts from I equal to 1. That is why I equal to 1 till I less than n, I plus plus, right? Then you're going to take hold of the first element in your unsorted part, which is a of I, and you're going to store in the variable int key equal to a of I. J is equal to I minus 1. This is basically, J is going to indicate the last element or the largest element in a sorted part of the array. You can get that by doing I minus 1. So now in other words, I can say from index number 0 to index number J, what part is it? It is your sorted part of your array. From index number, basically starting after J, basically what you have is basically your J plus 1, right? Or in other words, we can give it a name as I. From I to n minus 1 index, what is your part? This is your unsorted part of the array. Yeah, fine. Now this is where you're going to decide whether you should be shifting your elements. So while j greater than or equal to 0. Why that? Because you're doing decrement, right? And if j becomes minus 1, there is no point because that number minus 1 is not a valid index. So while j is greater than or equal to 0 and your a of j is greater than key, you are going to do what? A of j plus 1 equal to a of j. This line is basically doing the job of shifting your elements. What? Because you have to make space for a new element, right? If you have to make space for a new element, all the elements which are larger than the element which you want to insert needs to move to the right hand side, needs to be shifted to the right hand side, and this particular line does the job of shifting it, right? After you have finished this while loop, basically your element where you have to be in, where that new element needs to be inserted at the position of j plus 1. So your j plus 1 is equal to key. You will keep on doing this for all the remaining elements which are present in your unsorted part of the subarray, right? This algorithm is the entire insertion sort algorithm, right? So if I now run this, yes, I have the numbers sorted 5, 6, 11, 12, 13. I had taken a simple array, okay, as you can see, and I just called the insertion sort. Okay, now coming to the time complexity of the sorting algorithm. We've already spoken that this algorithm is a stable sorting algorithm, right? Second is time complexity, because obviously there are two loops. The time complexity is going to be O of n square, right? But what about the best case scenario and the worst case scenario? When would you have best case? Here also you would have a best case when your array is completely sorted. Let's say you want to sort in ascending order and your array is completely sorted in ascending order. You are going to run this particular algorithm only for O of n time, because there are not going to be any kind of swapping. Think about this when you actually have this, right? Though you have two loops here, Okay, this loop is going to run for n times. What about this? If the array or with the input, if you have it's already sorted, this particular while loop is never going to be true. If this is never true, this while loop never gets executed, right? So how many times your algorithm actually runs in the best case? Only for O of n times, right? So the best case scenario is O of n times. Worst case and average case, it is basically O of n square, which is your insertion sort algorithm. Are you taking any extra space to sort? No, you're not taking any extra space. So the auxiliary space complexity is O of 1. You're not taking any extra space. Only the space what you require to store the array, that's the only space you're taking. Other than that, there is no space required to do this algorithm. Okay, hope this helps.